Hello everyone. Here I'm going to present our paper which focuses on the effect of intra-team ties on team performance. We use a very interesting context, online games, to conduct this study. We are going to start from background and research question. Then, based on literature review, we propose several hypotheses. After that, we will show methodology and the results. Finally, we will discuss contribution and limitation. This research is motivated by the importance of teamwork and the effect of networks. Firstly, effective teamwork is very important for organizational success. Over 80% of companies use teams to perform tasks. Secondly, intra-team ties and intra-team networks can affect team performance because they can affect interactions among team members. However, despite a large amount of research on the correlation between intra-team ties and team performance, evidence for the causality lacks. Hence, we want to estimate the causal effect of intra-team ties on team performance. More specifically, our research questions contain three parts. Firstly, the average effect of intra-team ties on team performance. Take network A as an example. After adding one tie to network A, we can get network B1, B2, B3, and B4. We want to know, on average, whether adding one tie to network A can improve team performance, and if yes, to which extent. Secondly, we will estimate the heterogeneous effect of intra-team ties holding network structures constant. For example, network B3 differs from network A not only in the presence of the new tie, but also in the presence of cliques. Both the presence of cliques and the new tie can be the reason for the difference in team performance. Hence, we need to separate the effect of intra-team ties from that of network structures. Thirdly, we will test the interaction between intra-team ties and network structures. In this question, we allow variations in network structures. We adopt social network services analysis. According to SNA, a network consists of a set of nodes and ties among them. Previous research has developed several measurements for networks. We start from degree and density. Degree refers to the number of ties. Density equals to the ratio of degree over the number of all possible ties. For example, in network A and B, degree is 6 and density is 0.6. Both theoretical research and empirical studies find a positive correlation between the number of ties and team performance. To separate the effect of intra-team ties from network structures, we also look into literature on centralization, cliques, and structural holes. Firstly, centralization refers to the degree of inequality in the network. Secondly, cliques refers to subsets of several fully connected nodes within the network. For example, in network A, node 1, 2, 3, 4 belong to a clique. Thirdly, structural holes exist where a node connects two or more unlinked nodes or networks. For example, in network B, node 2 connects the small network of 1, 4 and the small network of 3 and 5. Interestingly, the effects of these structures on team performance remain some inconsistency. Firstly, the effect of centralization can be positive, negative, or null effect. Secondly, the effect of cliques are negative, but there's only one empirical study. Thirdly, the effect of structural holes on team performance can be negative or curvilinear. To sum up, current studies on the effect of intra-team ties have three main limitations. Firstly, they only use a small number of teams. Their findings may lack statistical robustness. Secondly, previous studies do not control the effect of network structures. For example, both the new tie and the disappearance of the structural holes can be the reason for the difference in team performance between network A and C. Thirdly, changes in the number of ties cannot capture the actual change in ties. For example, network B has 6 ties and network C has 7 ties. But we cannot get network C from network B by adding only one tie. At least 3 ties change. Tie between node 2 and 4 disappears, and tie between 3, 5 and 4, 5, 4. Hence, using density can lead to oversimplification. We propose 3 sets of hypotheses. Firstly, we propose that on average, intra-team ties can have a positive causal effect on team performance because in previous studies, the correlation are positive. Secondly, we control the effect of network structures by holding them constant. We propose that when teams have a low centralization, have no cliques, or have no structural holes, intra-team ties can have a positive effect. On the other hand, when teams have a high centralization, have cliques, or have structural holes, intra-team ties may not have a positive effect. In the third set of hypotheses, we allow variations in network structures. We propose a negative interaction between network structures and intra-team ties. To test our hypothesis, we employ a popular online game, League of Legends, as our context. This context has several unique advantages. Firstly, there are a large number of teams in the game. We can find sufficient number of teams with any kind of network. This allows us to carefully control confounding factors. Secondly, team formation in this game brings rich variations in networks. Friends can form teams together and non-friend members are assigned by the algorithms. This can help reduce the selection bias of non-friend members. Thirdly, variables can be quantitatively measured. There are common criteria for team performance, individual capability, and game difficulty. Lastly, an ideal game usually has 3 to 6 members, and teams in LO usually have 5 members. We identify intra-team ties according to players' historical gaming data. One intra-team tie between two players will be identified if the two players have finished more than 2 games together. Then we figure out network structures for each team. We first compute centralization for teams and categorize them into highly centralized ones and low centralized ones. Also, we figure out if teams have cliques or structural holes. Finally, team performance is measured by the game result, win or loss. Team members' capabilities are measured by their accumulated game points. Game difficulties measured by team members' ranking in the game. This table shows summary statistics of our variables. After dropping teams with missing values, we collect about 4 million teams. On average, one team has about 5 intra-team ties. We follow 4 steps to reconstruct our dataset. Suppose we have 5 teams. Each team has a network A, B1, B2, B3, and B4. Firstly, we identify pairs of adjacent networks. 2 networks are a pair of adjacent networks when they are identical except for only one type. Hence, network A and B1, A and B2, A and B3, and A and B4 are 4 pairs of adjacent networks. Then we use pair number to control pair fixed effect and delta type to differentiate between control group and treatment group. For example, for network A and B1, the pair number is PAB1. Then delta type for network A is 0 and delta type for network B1 is 1 because network B1 has one more type. Team 1 is in the control group and team 2 is in the treatment group. We repeat the process for pair AB2, AB3, and AB4. Finally, we combine all pairs of adjacent networks to construct our dataset. As shown in this table, network A belongs to 4 pairs. Thus, team 1 duplicates for 4 types. There are 34 kinds of possible networks for a 5-member team. We list them according to the number of ties in the network. Then we figure out all possible pairs of adjacent networks. In this picture, arrows list pairs of adjacent networks. For example, network 0 and network 1 are a pair. In total, there are 74 pairs of adjacent networks. After reconstruction, we get about 11 million observations. Here we present our models and results. In all models, we use team performance and dependent variables, capabilities, and difficulties as control variables. In Model 1.1, we find that total number of intra-team ties can have a positive effect. The result is consistent with previous studies. Then in Model 1.2 and 1.3, we test the effect of delta type on team performance. Before we control pair fixed effect, the coefficient is 0.18%. After controlling pair fixed effect, one type can increase win rate by 0.26%. Hence, we find that it is necessary to control pair fixed effect. Then we look into subsamples with the same network structure to test the heterogeneous effect of intra-team ties. We start from centralization. In Model 2.1 and 2.2, we look into networks with low centralization. In Model 2.3 and 2.4, we look into networks with high centralization. We find that after controlling pair fixed effect, when centralization is low, intra-team ties can have a positive effect, but when centralization is high, the effect is not significant. Similarly, in Model 3, we hold clicks constant. We find that when teams do not have clicks, intra-team ties can have positive effect, but when teams have clicks, the effect is not significant. In Model 4, we find that when teams do not have structural holes, intra-team ties can have a positive effect, but when teams have structural holes, intra-team ties do not have significant effect. In Model 5, we test interaction between three kinds of network structures and intra-team ties. We find that the interactions are all negative. The results of Model 5 are consistent with the results in Model 2, 3, and 4. This paper makes several contributions. Firstly, this paper estimates the effect of intra-team ties on team performance by controlling confounding factors. This helps fill in the research gap in the lack of causality. Secondly, this paper reviews how intra-team ties can interact with network structures. This may provide an explanation for the inconsistent results on the effect of centralization, clicks, and structural holes. In practice, this paper suggests that team managers should be mindful of the changes in the network structures when developing new intra-team ties during cooperation. This paper has two main limitations. Firstly, the mechanisms behind the effects remain unclear. Secondly, the external validity may be an issue. Hence, we consider the following aspects for future work. Firstly, we are going to test how the effects of ties may depend on the capability of the nodes and the rows. Secondly, in this paper, we do team-level analysis, but in this game, two teams are assigned as rivals in each game. By doing game-level analysis, we can know how the contextual factors can moderate our results. This is a presentation of our paper. Thanks a lot for your attention. Here is my contact information, and we look forward for your comments and suggestions.